Yay.
Wait a couple of seconds. So, Schiller undertakes research in the coatings and tapestry, whereby collaborations and developing 40 to 150 reports. The seminar is structural properties of materials, delving into what we can change. So we welcome Tara. Thank you very much.
Thanks, Pedro. Thanks everyone for tuning in. Now I can't even change my slides. Oh, it's finally decided to wake up. That's fine. So first of all, I'd like to acknowledge my team, and I'll probably do this several times on the way through. As an academic, you're as strong as the people around you. And I think it's worthwhile mentioning I have a pretty diverse and a pretty amazing team working with me. So it's one of those questions I always get. What are you doing? Why are you doing it? A lot of people tend to sort of box themselves into a materials base. I tend to look at the materials as basically a thing that the characterization uses to understand rather than the other way around. Any of you that may have seen The Office and stuff like that will probably kind of understand by the end of the talk what I mean by this. So a little bit about me. My master's is in applied physics. My PhD is in chemistry. The difference between the two is quite marked. I did physical vapor deposition of coatings onto polymers, and in my PhD I did synthetic chemistry in making polymer composite particles. Throughout I worked as a technician at the government research organisation in Australia, worked with an EU framework project. Yeah, so quite a bit of diversity. First postdoc out after my PhD was in nanotoxicology, again looking at characterization of uptake of largely metal oxide particles with that. With moving on from there, after about 2 years, I went to Monash, so from Queensland, and then went on to look at more photopolymerization. And for those of you in the audience doing chemistry, I learned a little bit about arrow pushing at that point. Not something I'd learnt because I just didn't do it as my undergrad. So that was a bit interesting in that sense. That contract basically finished up. And at the time, I was kind of treading water a little bit of trying to work out what I was doing. I met an amazing cardiologist that was doing his PhD and started to look at characterization of heart plaques, and I'll come to that at the end of my talk. I've done quite a bit with teaching and other bits and pieces, and 6.5 years ago we landed in the UK and haven't looked back since, I guess. So we postulate these to people. How do you know what something is? You know, we pick an animal. This cat is fairly hairless, by the way. He's 16 and a half years old now. We know that it's a cat. We know without running a DNA test, doing anything else, by looking at the cat, we know it's a cat. Image on the right, however, it could be anything. And realistically, it could be done by a lot of different techniques. I could have false colored this. I could have done a lot of things. So without knowing what you're doing and what you're looking for with some things, you simply can't get the answer. You're not going to stick the cat under the microscope by all means, and he probably won't sit still long enough to do that even as a 16-year-old cat, I can tell you that for free. So, you know, one of the big things for me is understanding and using characterization techniques. I largely look at soft matter, but one of the things I've done on and off in my career since my master's is look at coatings as well. But when we're looking at stuff, we're looking at the interfaces, we're looking at the surface, polymers, composites, biological material, and we're looking at change and evolution in the materials over time. So that can be either degradation or curing, kinetic change, and so forth. One of the things, like I mentioned about my team, we have a truly interdisciplinary team. So I have working with me in my direct team, engineers, chemists, physicists. I've got a microbiologist starting in October. So it's a really nice mix, but all looking at the same kind of output. It's a fantastic thing being able to sort of talk in that realms with it. Sort of last slide, I guess, on this sort of thing. One of the big things with me, and having been to Guadalajara, you've got excellent equipment and stuff. I did the full tour around and stuff. It's understanding how to use it, understanding what to do with it and how far it can be pushed. You know, one of the things I really like is the characterization from the nano through to the macro scale. So for me, that's also a big part of it. You kind of need to get an idea of where you're at. Obviously, you don't want to run every test on everything. It's laborious, but it's also a lot of it will end up redundant with it. I always like putting this picture up. How do you know if something's good? Well, it's system dependent, as I keep harping on about. So on the top left-hand side, we've got a nano bunny. This image to me in my PhD kind of made my day. It's furry, it's ugly and all that sort of thing, but it shows the extent of the coating of my polymer on my gold. Because of the surface imaging of the SEM, rather than running TEM, we could see exactly where the polymer was rather than looking at the electron dense gold, which is what the TEM was doing and drowning out the polymer. This image here, the one below it, is an image we took of the surface of a hydrated silicon network that we'd made. You can see by the scale here at 10 microns that this surface isn't very smooth at all. So it's not very consistent or anything else with it. The image on the bottom right, if we were talking about microscopy, would be too much contrast, too much brightness, and we get a white and black image. With the top right, we can see that there's a pretty little pattern in the middle. What we had was an interpenetrating network, and with the interpenetrating network, we etched away one of the phases to see the silver particles that we generated in situ here through a hexafluoroantimonate salt. The thing is, we don't really know if this is between the phases or in the phase that we etched away, but you know, it's still nice to get somewhere with things. I'm going to go through some examples. By all means, log up some questions. I'll answer as best I can. But yeah, this sort of just shows kind of the diversity of where we're heading. The results I present are, what's the word, either published or been submitted with things. So some of them are available on my Google Scholar. Some of them will hopefully be updated in the next few months, depending on how everything goes. And as we all know, and as Pedro just mentioned, COVID tends to delay things a little bit as we're looking at things. So following on from some of the work I did as a postdoc, I picked up on doing production of polymer networks. Then a coffee conversation, I guess, started something that we were keen on looking at with silicone networks. As I mentioned about my master's with the coatings and stuff, a couple of projects in that space, and that space will expand on. And again, one of those things with the characterization that led me into a different sort of soft matter and looking at cardiovascular disease. So Sergio's work, he's in final year now, and sort of hopefully done by, I think it is the end of the year. Sorry, I just got a couple of students finishing off at the moment. Sergio's background, he actually worked in industry with a company that made cyanoacrylate glues for a year after his master's, and then decided to come back and do a PhD. So one of the things that we've looked at with his project is not only the materials, he's worked in collaboration with a couple of good synthetic chemists I know of actually expanding on sort of some of that part with it. I won't go into as much of the synthetic chemistry. Whilst I know it, I just think there's some really neat stuff he's done and embraced throughout his project with the other part of things too. So I always go back to dental resins. When we look at cross-linked polymers, whether they're elastomers or thermosets with it, we want something that works in the application. So we don't want shrinkage. We want it to last the test of time. And, you know, dental resins and fillings and stuff, when they're photocured and stuff, you don't want them to shrink. You don't want them to pop out in the week and have to go back to the dentist. So application-wise, it's quite diverse. I mean, we've taken a step back and looking at this more lab-based in that sense. So we're just trying to move away from off-the-shelf monomers and trying to look at ways that we can improve our systems with it. So yeah, we've got a lovely network here. If everything worked and everything went perfectly, this is kind of what it would look like. This is done by adding a photo initiator, a catalyst in it, and cured at visible wavelength with it at 365 nanometers. So we basically throw the three things in and pop out comes the network. So we get an elastomeric feeling polymer out of the end of it. So what we thought was, well, can we react via thiomical chemistry and make a macromonomer out and then do the same sort of polymerization? So realistically, we're working with the same parts, but we're now looking at a system that's probably slightly more controlled. Do we get exactly the same things out? Yeah, it's more looking at as well. Yeah, you can see here by the picture the change in the system and stuff like that. Yeah, so I just saw Pedro's email pop up. I actually can't hear anyone, even though you can hear me. Unfortunately, I don't know what's wrong because the settings are the same for both the audio in both directions, so I have no idea. So when we look at the network change here, so we add the more random network here compared to the system we've made, we get quite a bit of a change in the performance of the material here. And this isn't unexpected because we've now started to control the system a bit better. So what's cool about this is then we can start to tailor the actual properties of the system. What we've done from here is looked at the kinetics of the systems and how much conversions occurred and stuff like that with it. The homopolymerization compared to the what do you call it, the acrylate compared to the thiol conversion too, that occurs at different times. Yeah, so we've got quite a bit of a changeover with the system depending on what we've actually done with it, which is honestly quite nice to see that it's in some ways the hypothesis worked quite well with this work. So, you know, so Sergio's done a nice job with these slides for me. Why do we care about what the TG is and why are we caring about the control of it? Well, we're looking at the difference in the acrylate functionality and the thiol functionality here. So basically, we're looking at the change in the cross-link density of the material. This is why we get the change with it. So yeah, so basically we get quite a different network for the same sort of things. So, you know, postulation of a question there. Is a higher TG better? In the case of acrylates, basically no. You don't get as much control over the network. you start to get tachiness, you basically get less curing. So as a general rule, it's a better idea of having things. The interesting thing here too is that when we increase the molecular weight, which to be fair isn't that much of a difference between the two, we get within reason a similar TG there. And the difference between the alternated two is much lower between the 575 and 700 compared to the 250 molecular weight with it. So, but you can see from the images, we're getting quite a bit of a changeover with the network system in the way they're curing and everything with it. So, which is quite nice. Yeah, so one of the things that we started playing around with a bit. So a colleague I know from McMaster University in Canada, Professor Mike Brook, does a wonderful job, has even written the textbooks on silicone chemistry. Some of the labs we shared in Australia sort of had some bits and pieces going on. And what I was more concerned with is making sort of materials out of them. The biomedical applications seems to be a good thing to do. Andrew too is a final year student, and again should be finished up by the end of the year as well. Yeah, so why do we care? Whether we're looking at contact lenses in the case of intubation for pneumonia, so putting the tubes down the trachea so that people can breathe. We want something that is stable and doesn't have much activity. So we want to make sure that it's not forming biofilms. We want to make sure that it's actually working in the way that we want with the activity and everything else with it. So yeah, so standard sort of thing. If you buy a Dow Chemical silicone, it'll be a platinum catalyzed reaction. This is done at temperature. It's an expensive catalyst. Most of the time it's done at temperature, I should add. It does start curing at room temperature, but it's not that quick. It's trying to look at ways that we could possibly remove the platinum or possibly palladium catalyst in this case. So again, one of the alternative reactions is using the Pierce-Rubinstein reaction. We add the Lewis base in, react it off, and basically it outgasses. So in the case, what we can see there is methane gas coming off. So when we so we've got a material that basically has a small amount of the Lewis base left behind. Yes, there's still toxicity issues, but in, I guess, low concentrations, there shouldn't be an issue with this. But when we look at the reaction, the beautiful thing about this is it all can be done at room temperature, and it's extremely quick as well. So we're talking, depending on the amount of catalyst, from under a minute up to a couple of hours, and it's done. Whereas a lot of the platinum palladium reactions are markedly longer. So what did we decide to do down this end? We decided to look at varying the monomer we were using for the silicone gels and looking at basically the reaction of those. Okay. So can you still hear me okay? Okay, beautiful. I'll keep going then. Yeah, sorry, it's ignoring my phone when I shouldn't be. Begin with slide 24. Okay, so yeah, moving away from the platinum palladium reactions, we decided to start looking into a room temperature reaction. The Pierce-Rubinstein reaction uses a Lewis base to react off, and the final material ends up with an outgas as well. So we kind of started to look at various monomers with this, primary through the tertiary sort of groups on them. And one of the things that we wanted to play around with was the outgassing. So probably should point out here, we can form foams from this. This was the paper we sort of, single paper in the literature we got to actually base this work off. And one of the things that we noticed, if we changed the solvent or we varied the catalyst concentration, as I mentioned, the time changes as well, played around with the reagents, which you can see here, the R group here changes from ethyl, propyl, N-butyl, S-butyl into methylpentane. So we've got, you know, primary through to tertiary here. We also played around with molecular weight as well. So one of the things we noticed too, it went off like an absolute rocket the first few times. Room temperature water bath, we did try ice baths because then it kind of slowed it down too much in that sense. But yeah, so quite a few things sort of playing around with to try and work out what we could get. So you can see on the left side, there's a nice fluffy, fuzzy looking thing that was quite brittle, to be honest. Basically could pulverize by hand quite easily. And then what we noticed when we played around, you can see here with our catalyst is sort of constant here. We played around with the what's it called? Monomer. Sorry, try that again. We played around with the solvent here. The hexane formed this partial foam, which is what we can see here. The heptane in with the lower concentration of catalyst foamed, and then when we use the heptane as well with a higher concentration, yeah, with a lower concentration of catalyst. Wow, not doing very well with that today. You can see here this nice transparent gel out of it, and this was kind of tunable as to how much you could get as to the changeover with it. I mean, these are obviously just 3 images, but at least sort of details what we were doing with this. So Andrew's done a really neat job of looking at characterizing the curing. What we did was look at the rheology and IR curing with it. What we noticed with some of the materials, they were going curing way too quickly to allow kinetics to be run with it too. So we kind of had to work out what we could do and what we could run to look at things. So you can see here we've got the different monomers with it. Yeah, so we've got some of the materials reacted too fast, some of them just didn't cure. They just basically get a little bit more viscous, but not go through completely with it. And you can see here the difference in the two. So the 1050 obviously has got a much higher storage modulus here compared to the 450, and here we're getting quite similar sort of reaction with it. So depending on the grouping off the ends of them, we were getting quite different reactions with the compounds. So I mentioned this before, biofilms form in lots of different places. Marine is an easy example from a visual point of view. But if you're putting a tube down somebody's throat and you want to make sure that you limit the amount of infection and try and keep this person that's obviously clearly really unwell, one of the things we need to do is make sure that the surface is not able to be contaminated by the biofilm. We've started to look into modification of the surfaces, but performance of them as well. We're kind of in the infancy still with that, working with a wonderful colleague in life sciences, Dr. Freya Harrison. But yeah, the intent of this, excuse me, is to basically get to that sort of point with it. So yeah, some nice sort of body of work with it. I didn't show all the results here with this, but we can control quite nicely how we form these gels. And it's reproducible. Andrew's been making these gels for quite a while, and every time he comes back to it for a different thing, it works exactly the same. It's actually quite wonderful in that respect. Yeah, so moving on to the next thing. Coatings. So I've kind of gone back into the coatings from more of an industrial point of view, but it comes from my master's in Australia. So in the UK, a research master's is a year. So from when is it, October through, well, pretty much submit again in September. In Australia, it's a full-time research project for 2 years. Pretty much like doing the first 2 years of your PhD now, I now realise. So a lot of the things to do with physical vapor deposition and I guess looking at Raman spectroscopy for graphitization of the surfaces and everything comes from that sort of respect. So yeah, sort of something fairly I didn't expect to go back and revisit. I think it'd be the best way to put it, but it's really, really quite enjoyable with it. So students here are Bruno Rodriguez and Steve Merritt. I inadvertently didn't put names on this one, so I apologize about that to both the students. From an industrial point of view, why do we care about coatings? Basically, it's got to do with the corrosion. We're looking at the electrochemistry here of what happens with the reaction with the oxygen. We're basically forming rust on the surface with the reaction of the solid iron into Fe2 plus with it. So yeah, so from steel industry point of view or longevity for most metals as well, we're really concerned about this. The coating itself too needs to provide barrier properties, and in some ways wear resistant for the lifetime that you're actually after it with. So yeah, so what Steve's doing is looking at nanocomposite coatings for barrier protection of steels. I don't have any of his work up. We're kind of the 11th hour of finishing a couple of things off with this one at the moment. But he works with the company Tata. Tata Steel UK is part of its operation is based at the back of Warwick campus, which is fantastic, working with such a good group of people that are very much on the other end to me. I'm very academic driven. They're very much not. So the synergies between overlaps are good. The differences are even better. So this works out sort of quite well. Steve's looking at PET nanocomposite films, and he's also looked into a lot of emulsion preparation. Now, with the emulsions themselves, that's quite a bit of an overlap of some of the things that Andrew does with his work as well. So yeah, so there's sort of quite a mix with it. I sort of thought I'd still include this. We're looking at whether you've got active or passive style coatings on things. So whether it's pathways to prevent corrosion, stimuli sensitive, or on the other hand, diffusion pathways to inhibit corrosion. So it really depends on how you approach things as to what you use with it. In our thing, we're looking at more the sort of passive way to do things, I guess. The chemistry and the I guess the cost associated with some of the active things wouldn't be industrially viable in what we were looking at with it. But yeah, so if you've got the substrate and you start getting any blistering, this same effect happens with plastics. When we look at, say, polyester boats, we get an osmotic blistering happening on that sort of thing. So if you've done study to do with polymers and things, I'd probably give that sort of an analogy where the attack comes from different pathways and stuff, and basically just causes catastrophic failure a lot of the time. And in this case, with what Steve's looking at, he's looking at packaging steels for food and stuff. I've left the title of this on here on purpose. Basically, all we're looking at here is the wear properties over temperature ranges of physical vapor deposition films. So diamond-like carbon, or tetrahedral amorphous carbon, as it's also called, is quite a common way to look at modifying materials. It's got really good properties. Basically, yeah, one of the big things that it doesn't have is good adhesive with it. So yeah, my introduction to this, one of the group I worked with in my master's was actually tool stills, and again, you know, a lot of what they're trying to do is improve the performance of the bits and pieces. Whether you look at your latest watch or anything else, we're still looking at the best way to do things. The beauty about physical vapor deposition too is the fact that you're not, if you're set up correctly, you're not stuck with geometry as much as other techniques either. So you can see the lovely tool bits there, which is quite cool. So I just wanted to put up a couple of the results. One of the things that we've seen, I use the royal we here. My students are doing the work and I'm basically here presenting it on their behalf. If we've got the amorphous carbon here, if you can see these nice grey channels down here, we get this sort of effect occurring. This is, you can see here, amorphous carbon sort of thing. We're looking at 500 nanometers. This one isn't quite as clear, but we can see the contrast with it. I think I probably need to reassure you it's there. One of the things that we do is look at the wear track, but measure it over a range of temperatures with it. So we're looking at what happens to the film, how it destroys, whether doping it with silicone helps, and yeah, so basically what changes we're seeing and how much I guess oxygen diffuses through the materials as well. Yeah, so good thing about this is the PVD technique, the high PIMs, worked quite well of improving the properties overall of the material, which was quite a nice sort of output of this. These TEM images of these just came out really well. One of the things I mentioned earlier was looking at tetrahedral amorphous carbon. So you use Raman spectroscopy to measure this, and we're again, we're measuring over a range of temperatures, as you can see here. We're looking at the change in the material. Sorry, just a sec. We're looking at the change in the material and how it's affected by the amorphous carbon and the silicon doped films with it. But you can see at room temperature, we don't have a heck of a lot going on. It's not until we move into the higher temperatures that we start to see the changeover with it. And you can see here, we've got some films that fail at lower temperatures than others. So you can see some are missing through here. So yeah, so it's not unexpected, but a heck of a lot of work by Bruno actually running this stuff through, which is quite cool. The nice thing about Warwick too, with the material stuff, the facilities we use with this are owned by the university, not by the department. So it means that they've employed somebody directly to help out with the instruments. We have the heating stages and everything as part of the equipment there, which is really nice with this. So yeah, and just some really, really nice sort of control over the amorphous carbon content, so the sp3. One of the things I didn't show here was the XPS results, which also verify everything that we're actually seeing with it. The oxygen diffusion doesn't happen at high temperature, but we do get the higher sp3 amorphous carbon content with it. So to move on to the last part of my talk, I kind of never expected myself to be doing anything in the health sciences. I did 6 months of one subject of Life sciences, so I did biology, first year biology, back a lifetime ago. Never did it at school, never did anything else. So never really expected to go down this end. But I'm really not. I'm still, in a lot of ways, still that materials person. So Rebecca's 18 months in, and about a year of that is COVID related. She's still made some really nice results and progress on this, but I'll talk a little bit more about the background and stuff. I don't know how well this translates into Spanish with atherosclerosis, but this is the blocking of the arteries. So where you get the calcification occurring and hardening of the arteries occurring. What this disease isn't new. This is CT scans from 3,500 years ago. So fairly recent discovery as well, as you can see. Just some statistics, hopefully not to frighten everyone of what they're eating for their lunch today. The coronary artery disease starts very early. So whilst it's always deemed an old person's disease, it unfortunately starts off quite young. It's basically it is the largest cause of death worldwide. You know, a lot of people die on the spot, and a lot of people don't get symptoms. That's really the big thing with this. So it's trying to get away, to actually look at this in a bit better way, I guess is the thing. It's an inflammatory disease. It's classed as anyone having a heart attack or stroke, even if they live through it, a lot of the time are quite unwell afterwards. So it's a long way of I guess, yeah, basically the inflammation occurs on the plaques. So this is a cross section down somebody's artery, and what you can see here where these arrows are, this is about the point in time where the unstable plaque, so the blockage, starts to break through. This here is about 10 millimeters across, to give you the idea. This blockage appears to be about 50%, give or take. And you can see here, cell walls reasonably intact, but we're starting to get breakthrough at that point. So rather than, I may have a quite gross photo next. I don't remember if I included it or not, and I apologize if I have. But yeah, the fibrous cap itself starts to thin, the plaque ruptures, and this basically causes a lot of problems in the system. And this is basically from a patient that's had that happen. Now, one of the things that's been a really big issue with heart attacks is that everyone goes to hospital when they've had one or they've got pain. There's not really anything to identify them at early stage. And, you know, a lot of the technology that exists, whether it's just an angiography, which is standard procedure, it's largely looking at what we can do in conjunction with what they do preclinical and clinical to actually move this so that people are not ending up disabled from things. So one of the studies we did that links into the back end of where Rebecca started is I ran into, as I mentioned, a cardiologist doing his PhD. What they were getting was this autofluorescence at around about 785 nanometers that they couldn't explain. So you can see here, these are mouse arteries. You can see here that we get a little bit of fluorescence from the stable plaque, but the ones that are vulnerable, we can see here, they glow without a better description of it. So you can see here, there's quite a bit of difference with the fluorescence emission from the vulnerable plaques compared to the stable plaques. So I'd like to point out that the patients that were randomized, anonymized and all that, they lived after this. So this procedure on the carotid, which is the artery that goes to the brain, was done and the person lived afterwards. So this is the waste product of them being able to be okay. You can see here that this is largely blocked, but even imaging this section that was cut out, you can see that there is vulnerable sections in it. So me being me, kind of did the whole, let's have a look. Maybe it's something to do with the heme degradation, because it changes color. Let's have a bit of a go. And weirdly enough, it turned out to be right. What we can see is the hemoglobin itself, the main peaks from it, and I'll come to something with it in the next slide, basically is what we're getting out of it. And I thought, oh, that's actually kind of cool. Not getting the ratios exactly right, so we needed to look a little bit more into it. You can see here that when the ones without the autofluorescence basically come out quite clearly as well. So I should point out too that we've had to run this on quite short wavelength. So anyone that's done Raman spectroscopy or looked into it, usually you have quite a problem at short wavelength with autofluorescence. We weren't having any, and we were running this at 413 nanometers off the top of my head. So with the hemorrhaging occurring, so the blackish brownish color occurring, it's a degradation of the heme. So hemoglobin is from the red blood cells. So once we get to the stage where we've kicked out the oxygen, we've converted to our biliverdin, and then we've had a secondary reaction with an enzyme, we've ended up with this bilirubin. So for anyone that doesn't want to look at these kind of porphyrin rings, if you look at the scale on the bottom, I'm sure everyone who's listening to this has given themselves a bruise at some time by some means, whether it's bashing a hand on the door or what have you. The color changes over time. So those byproducts of what goes on in a bruise is analogous to what we're seeing within the plaques. So yeah, so which was actually kind of cool in the end. Like any good person trying to verify anything, we ran everything possible to prove that we were actually on the right compound, to make sure that we weren't making something up, I guess is the way to put it. The beautiful thing about running a lot of these tests too is that we can see what's going on in them by, I guess, more traditional techniques. So these immunohistochemical is sort of more stock standard tests. So there's things that we can run called like a Prussian blue test right through. So there's quite a lot of things that we can do to also tick the boxes in a way that's understood by the medical field, rather than just by what I can see as as a physical scientist with it. So yeah, so I showed that image a minute ago. One of the things we're doing is using other techniques. Now, we've had a lot of support with this project, and I'm really amazed. From an interdisciplinary thing, this has just worked beautifully. We're largely looking at the histology, the markers, but we're also looking at the characterization with it. I've been really fortunate that I've picked up collaborators with a local hospital that's based in Coventry as well. It's about a 25-minute drive from campus, but we've been really fortunate that we've been able to continue this work over here and still collaborate with the group I've been working with in Australia. So yeah, so it's been quite wonderful in that respect. So I'm going to kind of conclude with a very simple statement. If you don't know what something is, you need to find out. And to be honest, no matter what you're doing, that happens to be the same. You know, if you're looking at process control and one end's not working, you need to work out why. So what I define as characterization and what somebody else might do, whether that's an internal industry test right through, it doesn't matter. It's still understanding what something is. So want to finish up. One of my students is on maternity leave at the moment, and I thought I'd mention here at the end. Anna is due to come back in October from her maternity leave with it. We've had a few people from master's students and stuff do a lot of proof of principle for us, which I'm really happy with, and come over on Erasmus scholarships. this isn't an exhaustive list by all means, but I work closely with the synchrotrons, both in Australia and here in the UK. I collaborate across campus at Warwick. I haven't listed a lot of people on here, to be honest. The Baker Heart and Diabetes Institute, the professor there, Karl-Heinz Peter, and the lab scientist, or the vet scientist, as we'll call him, that does the mouse work. They've just been amazing. Same goes with Chris Imray and Ruth Benson, the vascular surgeons at the local hospital here. I've got collaborations with colleagues in Indonesia. Yeah, so and a visiting fellow from Torino in Italy. So yeah, quite nice in that respect. And I'll finish up there, which should be about the right time for everyone, and I'll ring back.
Bien, antes de que me comunique de nuevo con la doctora Tara, les voy a pedir una disculpa, les voy a ofrecer una disculpa porque no había activado, se me olvidó quitarle el mute al micrófono, así que no pudieron escuchar la presentación que hice, pero esencialmente solamente leí lo que la doctora Tara nos envió como el texto que quedó integrado ahí en la página web. Así que hagan llegar, por favor, sus preguntas al chat. Creo que va a ser la forma en que nos vamos a poder
I'm just reading some of the comments before I comment on it.
Okay.
Fine,
Ella
fine,
está
beer and
leyendo
fish and chips.
directamente,
Thanks,
está
Elena,
leyendo
for that.
directamente la pregunta de la doctora Nena. Muy bien, la escuchamos.
So, Elena, you wrote the question about the cross-link density change. So it's got to do with the curing kinetics and how fast they cure. The what do you call it? The acrylates compared to the vinylic groups. So it's kind of serendipity, but it's something that's nice to be able to control. So you know, a lot of the reaction rates and stuff have been studied, but we've taken advantage of that. I think that's kind of the thing you're asking. I'm happy for you to comment on that if you want.
Pedro, dices que la doctora no nos puede escuchar, ¿verdad?
No.
Ok, ya le contesté entonces por escrito.
Sí, ya vi que ya contesté. A ver, déjame ver si me puedo conectar de nuevo con ella acá por el tono.
Es que ella fue muy cándida al decir,
Hello?
sí fue. Yes.
Sí.
Yeah, I can hear you.
Hello?
Oh, can you hear me, Professor?
Yes, and I see Elena's answered again. I'm fine.
Thank you very much. And I do appreciate how candid you were in your answer, because sometimes when we find serendipity.
Yeah.
Yes.
A ver, Nena, no te escucha. Sí,
okay,
tienes que estar acá por el teléfono.
Okay.
Les pido una disculpa a todos los demás. Voy a hacer un par de preguntas directamente a la doctora Schiller, pero la estoy llamando por teléfono. De hecho, voy a prender mi video nada más para que qué malabares ando haciendo, ¿no? Aquí con el teléfono y tal. So, Tara, thank you so much for your presentation. It was very, Elena, Doctora Marilena, thanks that you know the candid part of your answer. Because she was asking about the serendipity of the system that was cross-linked in the first, you know, maybe the work with Sergio?
Yes.
Okay, so in the second part, you talked about the silicone. The silicone, not, you know, without using the platinum.
Yes.
You are changing things in order to obtain, you know, the very kind, you know, the same properties of the material. But what about the cost? In economic terms, what is, you know, so your solution is cheaper? You know, is very expensive, the platinum. But what about yours?
So it is cheaper, but it's also cheaper from an energy point of view because you don't need to heat the samples. So the catalyst works at room temperature. So it's sort of a two-pronged effect. It's not as expensive as buying the platinum. But I mean, we've just done a rough study on market rates of it, of what we can buy. I mean, obviously we're not buying in bulk.
Okay, that's it. But I will ask you something about the the steel, the coatings of the steel. What about you are working with the polymer, but
Yes.
you are using it with the steel. What about the to avoid the good adhesion of the polymer to the steel? You are evaluating that kind of property.
We will be in some of the work. So the thing with the polymer coatings on the steels, they're a multi-layer effect. So we're examining one of the layers that we can modify a lot more easily. So it's an interesting question because that does come up quite a bit. And that was one of the first questions I actually asked. They've got to be the polymer coatings need to be thermally stable enough because they apply kind of like a hot roller on it. I can't think of a better way to describe it. So I don't know. It basically goes through a rolling machine. So basically kind of like a ribbon machine.
It's different. It's a challenge, no?
You
can have a new material that works perfectly, but it's hard to put the coating through the steel, and I think about the steel. Steel is big parts, no? We are not talking about the small parts.
No.
I don't know.
From a chemical engineering point of view, the process is really, really important here. So it's an interesting one because you're into facial science, so is in how we bond things together through to looking at the tribology and the wear and stuff is really, really crucial with this, as well as the barrier properties, so the permeation. So for example, if we were to put a nanoparticle in like say silver for antimicrobial reasons, silver can also be conductive. So this might end up corroding our steel.
Yep. So I will ask you something different of the same project. What about the funding? You have to spend money, but now you work with the industry, and Warwick has another, a lot of projects working with the industry. What about they spend a lot of money in this kind of project? You don't have problems with funding? How? And the other question related to that is how fast you can give the results, because they are expecting that funding work as soon as possible, I think, no?
So there's I guess there's two different ways to answer that. One is this short-term comparison. So if we've got something and we're trying to fix a problem, we can look at it as a short-term, run a bunch of tests, whatever that happens to be, and produce a result. From that, we can then turn around and go, oh, but what if we did this? That becomes a long-term, more research problem with the company. So in companies like larger companies, and to a point, some of the SMEs that take on PhD students, they realize that the component of doing the PhD actually plays a part in their development. Because for the company to pay towards the PhD, it's quite a equitable result. So it's quite cheap for the company.
Yeah,
but within
I can imagine that.
Yeah, so within the UK, we have kind of a thing like Conaseat where we get government funding as well. And we can also have somebody that's employed by the university but works at the company. So there are different sort of funding mechanisms to do things as well.
And it's working all together, right? Right now, we have some problems because the government is convinced that they cannot fund a project that is involved with an industry, with a private industry, because they say that they have their money, so they can spend some of their money in doing research, and the funding cannot be from the government. It's quite difficult to have these kind of projects here in Mexico, but we are we're testing, no? They have some,
so that's an interesting one.
political.
So the attitude of the government here is that we need to keep primary industry going, to keep the economy happy in the country. So the government has put forward calls for research within companies only, without the universities as well.
Right.
So I can probably send you links of what they've actually done recently with a couple of these things as well, because they're press releases. But I think yeah, unfortunately similar things have happened in Australia where, oh well, the government, we don't need to fund that. That's got to come from this fund.
Mm-hmm.
Yeah, I've seen similar things like that in places like in Australia. There are certain things that you can't do with industry funding. So if I get a industrially funded student, they need to be a UK resident.
Okay.
So yeah, so unless of course the funding comes through another means, which, you know, we've got such a mix of sort of schemes and stuff that, yeah, it's it's quite a different thing. We've also had, I guess, post-COVID, had a lot of money directed towards school and education, and that money's come out of the university sector.
Mm-hmm.
So we've got less access to research funds at the moment because the money's gone into educating the children that missed out on school.
Yep.
So
the next question is related to that situation. You know, we have funding from the industry, and they understand the results in a different, you know, in a different way that the academic,
yes,
you know, the thing that we are used to do. But right now, I'm thinking about, what about the students? What about the PhD students with funding from the industry? They have also goals in the academic, you know, in the academic way of doing things. They have to publish papers, but then the papers cannot be published because they are working with the funding of maybe some idea that they want to be a patent, not a paper, not a free information for everyone, just for the industry. How come a PhD student from Warwick can get some recognition also in the academic way we are doing things?
I think we'll call that luck, Pedro. I've been really fortunate. So I've worked on PhD theses, and some of my students will have part of their thesis embargoed. Some of it will be published, some of it won't come to light for another 2 or 3 years. So there's been components of the work, and the companies have been fantastically good to deal with in this respect, with regards to publishing and everything like that. I've got projects where we simply don't publish at all. So
Yep.
and that's not an unusual thing either. But all the projects I've been involved in, I'm really quite thankful that people are publishing from them.
I asked that because you know the number of journal papers that you have and the number of reports that you have. You have 3 times the number of reports than the papers that you have published. That's why? Because you work more for the industry?
Yeah, I have at times. So it depends on where I am at what I'm doing as well. So I've had times where we simply haven't been able to publish stuff, and it's gone into private sort of stuff. But most of my PhD students have published, will publish, or publish part of their thesis because of those reasons.
And what about this kind of stuff that you have published? They have sometimes no connection. No, you are the materials girl from Twitter account, no? But there is bio, the life sciences stuff, the bio stuff, with the toxic stuff that you have in the postdoc thing, and then you have the polymer synthesis and the chemistry stuff. If you have you read your resume, you think this girl is working with different things. What kind of conference you go to? No. to the polymers, to the materials of life sciences?
So
what is the experience?
I must admit, I've been to a cardiology conference, and that was actually kind of fun.
Okay.
A research conference. I largely go to materials-based or polymer-based conferences. My background is characterization.
Yep.
So
and that's why the last part of your seminar is that, no? It's characterization applied to life sciences. It's a different way to do it. Sometimes I think that you know, the doctors or the medical science is like the black box you were talking about at the beginning of the seminar, no?
Yep.
They use drugs and they expect a result. If the result is not there, so they change the drug. No, it's not quite the, you know, analyze the chemistry of it, or be more patient about that, because, you know, the protocols of the medical sciences, they need results, like the, you know, COVID vaccine. No, we need results right now because we need the vaccine for everyone. But to give this approach in your material science, you know, way to do the things in life sciences is quite interesting. So Dara, the time is over for us. I thank you so much for being here. Really, we have some issues with the technical stuff, but we have the opportunity to hear you. We listen to you very clearly. So, so I thank you so much for being here.
I think I just blame it on Friday night in the UK on that one, because I've got no idea why it's not working.
So maybe it's not time to go to the pub, like Dr. Elena said that. Cheers, Tara. Thank you so much for being here.
Thanks very much, Pedro. Thanks everyone for listening.
To talk about with you.
All right.
Thank you so much.
Thanks. Bye.
Bien, les agradezco mucho a todos que hubieran estado presentes en esta presentación. Les ofrezco una disculpa por la introducción tan accidentada que tuve. No había notado que no había quitado el botón de mute, así que espero que ahora tengamos oportunidad también. Siempre dejo los vínculos en la página web para que puedan acercarse a la doctora Tara y a la Universidad de Warwick. Sí, tienen una forma distinta de hacer las cosas, ya lo notaron. Hay dinero invertido de empresas. Recuerdo haber estado ahí y ver logos de empresas de automóviles muy importantes y hablando de cantidades impresionantes de dinero para financiar cosas que tienen utilidad, y acercarnos a ese tipo de aplicaciones va a ser muy interesante. Bien.
Pedro, te voy a interrumpir.
Sí.
Gracias a ti por la gestión. Traerte a alguien de Europa a darnos un seminario en viernes en la tarde. Vean el cambio de horario. Ella debería de estar echando chelas en el pub. Entonces, de veras, muchas gracias. Todas las maromas, el haberle marcado tú